Hello everyone, how are you? So I am Vipin Kumar and I welcome you all to the India's most comprehensive preparation platform for GATE and ESE. So I hope yesterday we had a good session on IC engine and refrigeration, right? And I got some answers in the Telegram group, the homework that I gave. So today we are going to continue the same thing. This is also a practice session but on power plant and psychrometry. Okay, so we will start with power plant. We will cover performance parameters, Rankine cycle, gas turbines, and then we will move to psychrometry. The part of refrigeration we covered yesterday. I hope you were all there, right? So Kanil, yes, good evening. Did you post the answer yesterday? Because I think you did not post, right? Did you solve them? So should we start? Okay, just I'll take 1 minute for some few announcements. So there is a Achievers series for GATE 2023 that you can get. And hello Lakshman, hello, hi. Okay, so there is a Achievers series. If you are still preparing for GATE 2023 and if you are in the beginning or the middle of your GATE 2023 preparation, then you can join Achievers series. Okay, and there is also I think it's a workshop that the last 121 days strategy for GATE 2023. Okay, no sir, I forgot. Okay, it's okay, you can try that. I posted the answers as well. Some people did that, so I posted the answer there. Okay, good evening Ayush Session. Thank you Meenu. Okay, so if what should be your last 121 days or like 120 days strategy for GATE 2023? How to proceed for further? Okay, so that workshop is on 4th of October at 8 p.m. So do not forget to join. And also there is a free GATE workshop, rolling workshop for the guidance of GATE aspirants. Okay, so you can find the details for the next workshop in the description box, and you can also find the link to register. We also have a rolling scholarship test for people who have financial issues. You can get up to 90% of scholarship, okay, for GATE preparation. So you can also register for the scholarship test and see when is the next scholarship test. Okay. And finally, we have a GATE preparation free ebook. You can download it from the link that is given in the description box. Okay, a brief introduction. So I have around 4+ years of teaching experience. I have done my MTech from IIT Kharagpur, my MSc from Politecnico di Milano, Italy, and I have around 3.5 years of industry and research experience. My area of expertise, as you all know, is thermodynamics, basic and applied, as well as heat and mass transfer. Okay, so now it is time. Let's move on to the question session, to the practice session. Okay, so let's start. Should we? So I would expect everyone to solve the questions. Okay, be one step ahead than me. Whenever I am, good evening Anita. Whenever I am reading the question, you try to read it, you try to note down the data, and you try to solve it before me. Even if you know the process, put the values in your calculator and give me the answer in the comment box. Okay, so let's start. Let's start with the first question on power plant. This is performance parameters. Okay, now what is given? We have a thermal power plant that consists of 2 6 megawatt units. Okay, there are 2 units that produces 60 megawatt, and then we have one more unit that produces 30 megawatt. Okay, and this one 60 megawatt is running for 8,000 hours and 30 megawatt is running for 2,000 hours. Energy produced by the plant, actual energy produced is 876 into 10 to power 6 kilowatt hour per year. Maximum load, we will consider maximum load as equal to the plant capacity. Sometimes what happens is that the maximum load, there is a certain plant capacity, but maximum load is less than the plant capacity. Okay, for example, the maximum plant capacity is 300 megawatt, but the maximum load, the plant capacity is 300 megawatt, but the maximum load is 200 megawatt. So you do not go above that. Okay, but in this case we are assuming that the rated capacity and the maximum load is same. Okay, so now let's say if we talk about load, the power. Okay, the power. So when we talk about power, so we have 60 megawatt of 2 plants. Okay, and we have 30 megawatt one plant. So what is the maximum power that you can get from this? Is 150 megawatt. This is the maximum power that you can get. Now in this particular case, maximum power is also equal to rated capacity. Sometimes rated capacity is higher. Okay, so this is the maximum power or maximum load. Power or load, we say it's same. Okay, it's two ways of saying the same thing. Okay, so maximum load is this. What about energy? Okay, energy produced. Energy produced. So, and this is in megawatts, right? Now energy produced is how much? So we have 60 megawatt into 2 plants, and they are running for 800 hours in a year. Okay, so I don't know how much is this, you can calculate. And then 30 megawatt one plant, and it is running for 2000 hours. So whatever you will get, this is the maximum energy that can be produced in this plant. I don't know how much is this. Can you calculate and tell me how much is the total? Okay, now the first thing that they are asking is plant use factor, and the second is load factor. I hope you all know how to calculate this. So okay, so first of all we need to calculate load factor. Okay, load factor. Load factor is defined as average load. Okay, this is 960 gigajoule per year. Really? And then it is maximum load. 12 and 8. Okay, now tell me what is the total so that I can write it here. Okay. So load factor is maximum average load by maximum load. Now load is in megawatts. Load is power. Okay. That is 1020 gigajoule per year. Okay. 1020 gigajoule per year. Okay. Now let's calculate first load factor, average load upon maximum load. Now maximum load is 150. What is average load? So the energy that is produced in a year. This energy is basically produced in a year. Okay. So what about power? So power, to calculate power, what we need to do? This is kilowatt hours per year, and we have 8760 hours per year. Okay, so now what you get, you will get in kilowatt. You will get in kilowatt, and this is in megawatt. This is in megawatt. So you can convert anything. So we can also divide the denominator by 10 to the power 3. So now this will be in megawatt. So very quickly tell me how much is the load factor. What is the load factor? 876 is the average load. It is the average energy produced in a year. We divide it by the number of hours, you will get the average load. Okay. So what is the load factor here? Can you see that? Can you see that? Average load. What is the load factor? How much is the load factor? .67 is correct. Okay, so it will be 100 by 150, and this is 0.67. Now there is another term that is called as capacity factor, which is average load upon rated capacity. I hope you all understand. Yes, Kenil, that is correct. 0.67. I hope you all understand what is the difference between maximum load and rated capacity. So for example, I have a plant and it has a rated capacity. It can produce. I am saying that my rated capacity is 400 megawatt. So you can produce 400 megawatt, but maximum load sometimes is basically less than the rated capacity. So it is what you are actually, that is the maximum that you actually take out from that, okay? So always maximum load is less than or equal to the rated capacity. In this particular question they have given, they are the same, okay? Maximum load as equal to plant capacity, okay? So load factor is 0.67. Now the next is plant use factor. What do you mean by plant use factor? So plant use factor, okay, let me write it here. This is question number 2 and this is for homework. Okay, so it's the same. You have to calculate load factor and capacity factor. So this you can do, but I am just solving this question here. Plant use factor, okay. So plant use factor. Now this is the average energy produced in a year and then maximum energy produced in a year, okay? So average energy is this one. This is the average energy that is produced in a year, and maximum is, we just calculated, gigajoule per years, okay? So average is 876 into 10 to the power 6 kilowatt hour per year, and this is something that you calculated, gigawatt hour per year. So you can convert the units, you can convert, and answer is 0.85, 0.86 I think, no, 5. 0.86, yeah, that is correct. 0.86 is correct, okay? 858, so 0.86. Canal. So this is 0.86 when you convert the units. Okay? Yes, that is correct. Where is everyone else? There are more people watching. Anita, Meenu, try to solve it. Okay, try to. Now we will. I am assuming that you have already done power plant. I am assuming that you know the formulas, you know the concepts. Okay. Our focus is on the numerical part. Okay. Now this is your question number 2. That is for homework. We have to calculate load factor and capacity factor. Here, the rated capacity and the maximum load is different. Okay, so just take care of that, and so very easy question. Very easy question, okay? So try to solve this, and let's move to the first question of Rankine cycle. Okay, now it is a okay, so it is a Rankine cycle question. We all know Rankine cycle. Okay, just circle that question number 2, otherwise it will be, yeah. Okay, so this is your homework. Okay, right? Now Rankine cycle is also called a steam cycle. Okay, what do we have? We have a boiler, we have a turbine, we have a condenser, and we have a pump. Okay, now let's draw the PV diagram. Let's draw the TS diagram. Okay, TS diagram. We can also draw PV diagram and TS diagram. Okay, now what is happening here? So now let's start with the turbine. Let's start with the boiler. So let's say this point. Okay, so this is 1 to 2. This is pump. Okay, and then it goes into boiler at a constant pressure. So this is constant pressure. So we are adding heat. We are adding heat at constant pressure in the boiler. Q in the boiler. Now what we are doing in a general Rankine cycle, what we are doing, we expand it to the lower pressure, but it is a reheating cycle. What we see here is a reheating cycle. So what we do here, I hope you are all aware with this, right? Now what we do here is, first of all, we are going to expand it in the turbine, then we are going to reheat it one more time, and then it will come back to the lower pressure. Diagram is not as per mark, but I hope you all understand what I am trying to do here. Okay, so this is 2 to 3 is boiler. Okay, point 2 to 3 is boiler. Then 3 to 4 I have expanded in a turbine. Okay, so I will get some work output. Then it goes back to the boiler. So 4 to 5 is also heat added in the boiler. This is also heat added Q in the boiler. Okay. Then 5 to 6 is again the expansion in turbine. Again the expansion in turbine. Sir, what are the important theory questions from power plant? Look, Rankine cycle is, I think, the most important and the most frequently asked topic in power plant engineering. If you analyze the questions from all the previous year, then Rankine cycle, the questions that have been asked from the Rankine cycle is the most. Okay, so this is the then gas turbine. Very simple question you will get. Okay, so but Rankine and gas turbine, which is Baraton cycle, they are the most important. Okay, in GATE. Now, so what they are asking thermal efficiency of the plant neglecting pump work. Thermal efficiency, I need to calculate neglecting pump work. Okay, so now I think I have left some space here. Yes, so I have drawn the diagram here. Now what is the efficiency? Let me write first here. Efficiency of any cycle is equals to net work upon heat supplied. Okay, net, something wrong with the value of H3. H3 is 30.3095. I am sorry. Yeah, it is 3095. Okay, it is 3095. Okay, yeah, right. So for efficiency for any heat engine or a heat cycle, work producing cycle is desired effect upon energy supplied. Desired effect is work output, energy supplied is heat transfer. Okay, now where you are getting work and what heat you are supplying. So as I have already told you that you are getting work in process 3 to 4 plus process 5 to 6, and heat you are supplying in what? You are supplying heat in 2 to 3 and 4 to 5. Is that correct? So if we know this much, then let's try to calculate the thermal efficiency here. Thermal efficiency of Rankine cycle is equals to net work upon heat supplied. So net work is happening from 3 to 4. So H3 minus H4 plus, then it is happening from 5 to 6. Okay, so H5 minus H6. Is this okay? Then heat supplied. Where you are supplying heat? You are supplying heat from 2 to 3 and 4 to 5. Okay, so H3 minus H2 plus H5 minus H4. Okay, now all the values are given in question. Steam leaves the boiler and enters the turbine at 4 megapascal. Okay, so this pressure is 4 megapascal and the temperature is given 350 degrees Celsius. Enthalpy is also given H3. Then after expansion in the turbine, H4 is also given. The steam is reheated again to 350 degrees Celsius. H5 is known to me, and then expanded back to this lower pressure of 10 kilopascal. So H6 is also known. Okay, and they are saying neglect pump work. So we have neglected the pump work. Okay, so minus pump work, which is neglected. Do you need to find H2? No, pump work they have said it's neglected. No, in the question they have said neglecting pump work. Okay, 41.1 seems to be correct. Yes, 41 point. Everything you know. H3 you know, H4, H5, H6 and H3. No, this is H3. Okay, so H3, if you are neglecting pump work, that means H3 is equals to H2. Okay, yes. If you are neglecting pump work, that means H3 is equals to H2. Okay. So very quickly solve it and tell me, Canel, are you also getting the same answer? 0.411. H1 आएगा ना? Yes, H1 आएगा ना? H1 is given. H1 is 29.3. I am sorry. I am really sorry. H1 is equals to H2. My fault. That is why diagram is very important. Okay. This diagram is important. Yes, that is correct. Okay. Now next question, it is the extended question. Enthalpy, the same diagram. Enthalpy at the pump discharge H2 is. What is the enthalpy at the pump? What is H2? How much will be H2? So pump work will be equal to H2 minus H1. Okay. Now what you are doing? You are giving some energy to the pump. Okay, some external energy is given to the pump. How much is H1? H1 is equals to 29.3 kilojoule per kg. Okay. VDP is only when we assume it is isentropic. Okay. And they have already said that specific volume nahi diya hai. Yes. Specific volume is also called as assumed to be negligible. Okay. Now, you can only see the options and calculate this. It is assumed, this question is assumed to be solved with a different approach. Okay. So when you see the options, you see, look, H1 is going in, pump is there. You are giving some energy. So H2 for sure will be higher than H1, isn't it? Now if you see the options, it is 0.33 kilojoule per kg, 3.33, 4 and 33.3. So can you tell me which one is the correct answer? The enthalpy of the what is entering is H1. H1 is 29.3. Okay. Now when it is entering, so you are giving more energy to it. So what will be H2? It will be more than H1, right? 33.3 is the correct answer. Yes. Okay. Now let's move on to the next question. Now in the Rankine cycle, regeneration results in higher efficiency because. Can you tell me the answer before I go with the explanation? I hope you have done Rankine cycle. Can you tell me what is the right answer? 5 is C, that is correct. Okay. So let's say this is your Rankine cycle TS diagram. Okay. YB, heat is added before steam enters the low pressure turbine. That is reheating, no? Kameshwari, Canel, what B? B is what? Yeah, C is there, right? Bhavya, okay, Bhavya is correct. Canel, B is reheating cycle. I am going to explain this and so many doubts will be clarified here, okay? TS. So a normal cycle looks like this. One to 2 is pump, 2 to 3 is boiler, 3 to 4 is turbine, Q in and Q out. Okay? Yes, that is B is reheating. Now what happens? Look. Efficiency when we say of a Rankine cycle, if you calculate it is mean temperature of heat rejection and mean temperature of heat addition. Okay. Now, if you want to increase the efficiency of Rankine cycle, there are two ways. Option D is also a result of reheating. Total work delivered by the turbine increases. Yes, total work increases. But heat also increases. So efficiency you do not know is going to increase or not. Okay. I am going to tell you right now. So what happens is Now if you want to increase the efficiency of the Rankine cycle, there are two ways. Either you can decrease the mean temperature of heat addition. Okay, you decrease the mean temperature of heat addition. So how do you decrease that? You decrease this temperature, you decrease this. You decrease this temperature. But this is limited. What is the lowest temperature at which you can reject heat? It is the surrounding temperature. You cannot reject heat. I hope that it is clear what I am writing. Okay, so you cannot reject heat. You cannot go below the surrounding temperature. So you can reduce the temperature of heat rejection, but you cannot go below the surrounding temperature. So this is restricted by surrounding temperature. Now the second way of increasing the efficiency of Rankine cycle is increasing the mean temperature of heat addition. Okay, if you adding more heat at high temperature, then efficiency will increase. Now what are the different ways of this? So now what is our objective? Our objective is to increase the mean temperature of heat addition. Okay, mean temperature of heat addition. Now we can do this in two ways. First, adding more heat at high temperature. Okay, when you add more heat at high temperature, then the mean temperature of heat addition will increase and the efficiency is going to increase. Now how can you do that? So what you can do is you can increase the pressure of boiler. Now your pump is going to pump to a higher pressure and this pressure will increase. So this is now your boiler pressure. So pressure and temperature in the boiler has increased. So now you are working at higher temperature. Now you are adding heat at high temperature. Okay, you are adding heat at high temperature. Okay, but there is one more thing before I tell you this. There is one more thing, I'm sorry, because I should go in a flow so that you will understand it better. Okay, now, okay, so the first thing that you can do is you can do superheating in the boiler. You can keep heating it. So what you can do, you can go to higher temperatures here. T3 is much higher, but there is a limit. Okay, so what you can do, first thing is superheating in boiler. Okay, so इससे you can increase your T3, and when you keep doing superheating, if T3 is much higher, then overall the mean temperature of heat addition will increase, because what is mean temperature? T3 plus T2 by 2. So if you increase T3, then the mean temperature will increase. But again there is a problem. What is the problem? That there is a material restriction. All the materials, if boiler has some component, they can only sustain to a particular temperature. You cannot go above that. Okay, so the higher temperature is restricted by the material construction. Okay, the temperature that they can handle. So somehow the higher limit is also fixed. So T3 is also fixed. Okay, so T3 is also fixed. You cannot keep superheating. You cannot keep increasing T3. Okay, so this is restricted. This is restricted by, I hope you are able to understand what I am saying. If any doubt, you tell me. Okay, restricted by material construction, material limit. Okay, now second thing. Now what you do, first point was superheating in the boiler. Second is increasing the pressure in the boiler. Now this is the step. Okay, so now you increase the pressure and you go like this, but you have to stop here because the maximum temperature limit is fixed. Okay, maximum temperature limit is fixed, so you have to stop at the same temperature. Is this clear? Now when you do that, then what happens? Now it goes into turbine. So when it goes into turbine, so now you see your you have more moisture, your dryness fraction is decreased. Okay, so second way is increase boiler pressure. So when you're increasing boiler pressure, your mean temperature is increasing, no doubt, because now you are adding heat at higher temperature and pressure. But the problem that is happening is that its dryness fraction is reducing and more moisture at turbine exit. I know I am hiding something, let me, okay, turbine exit. Now what is the third way? So what you can do now? Now what you do not expand it completely. You expand it slightly and then go to reheating. Okay, so now what you do is instead of going like this, you expand it slightly and then go reheating, and now you come here. So the third step is reheating. Now because of reheating, what is happening? Your turbine work is increasing, no doubt. So you may assume because turbine work output is increasing, my efficiency is increasing. But you have to give extra heat in the reheating. This portion is extra. So your heat supplied is also increasing. So heat supplied, I hope you are able to see this. Heat supplied is also increasing. Now I am not sure if my energy, if my efficiency, which is net work, one second. Now I am not sure that, because both are increasing. Okay, now I am not sure if my efficiency is increasing or not. It depends on other parameters as well. Okay, only reheating and will decrease. Efficiency will decrease? No, it's not true actually. Most of the cases, yes. That is why you do not do reheating. You do not do reheating alone. Okay, you basically, the combined cycle is a combination of regeneration, reheating, intercoolers and all these things. Okay, but this is not entirely true that if you are doing reheating, efficiency will decrease. That is not sure. Okay, it may increase, it may decrease. Okay, now this is the first portion. I was saying there are two parts. Okay, so this is the first part, and this first part is when you are adding more heat at high temperature. Now second part is what? How do you increase this? Second part is, I wanted to increase T mean in, right? So first part I have seen, add more heat at high temperature. This is my first part, and I have shown you 3 methods to do it. Okay, 3 methods to do it. Second is add less heat. I know I am taking a lot of time, but a lot of people are really confused about what is the utilization, why we do reheating, why we do regeneration. Okay, and what is the difference? They confuse reheating with regeneration. Okay, so add less heat at low temperature. Okay, so if you are adding less heat at low temperature, so what is going to happen? Your temperature, your mean temperature of heat addition is also going to increase. Now for this, we do regeneration. So why regeneration? Now what do we do in regeneration? In regeneration, what do we do? TS. Okay, so exit of turbine and entry of combustion chamber. What? So exit of turbine, what I mean, I did not understand what you are trying to say. That is gas turbine, okay? Not this. Okay. So now what we do, from turbine, I take some part of it. And then send it to the boiler by using a feed water heater. Okay. So I take some part and I send it to boiler. Okay. Then rest of it goes, and then some part is gone again to the boiler. Okay. So here also we have pumps. So something like this you diagram you get. That's baritone, that's gas turbine. That's what I was saying. What is the number of applications of thermodynamics? You mean weightage? It's around 3 to 4 marks in GATE. Okay. Yes, that is what we use: open feed water heater, closed feed water heater. Okay. So now what we do not expand it completely in turbine, because turbine exit is coming at a very low temperature and pressure. We slightly bleed in between, which is at higher temperature, and we send it to the boiler by using a feed water heater. Okay. Then we bleed it somewhere in between. It is also at higher temperature. It will go to the boiler. Now we are rejecting heat. We are rejecting now less heat. In condenser, only small portion of the turbine inlet goes. Okay. If some 100% is going in the turbine, so only some part, only 40 to 50% is going in the condenser. So whatever heat is rejected in the condenser is basic. We have reduced that heat, and by doing that, we have increased the mean temperature of heat addition. And that is why the whole purpose of regeneration is increasing the average temperature of heat addition in the boiler. And that is the reason that the efficiency is increasing. Okay, so you do this, and this will increase the efficiency of the Rankine cycle. I hope it is clear to you. If it is clear, very quickly tell me in the comment box, or if you have any doubts, then tell me, and then we will move ahead, because I took a lot of time in this question, but it is a very important and very confusing question for a lot of people. Okay, they just try to remember these things. Okay, reheating is this, regeneration is this, but there is a certain significance behind it. Okay. Okay, now let's move ahead to the next question. We all know this question. We have two cycle coupled in series. Their efficiencies are given 30% and 20%. Overall combined efficiency I need to know. Very quickly tell me. Overall combined efficiency is N1 plus N2 minus N1 into N2. So what is the answer for this? We all know, okay, 0.3 plus 0.2 minus 0.3 into 0.2. Okay, so this is how much? I know this. Yes, this is 44%. Yes, 0.44. Sachin, university exam, they give you steam tables in the exam. Okay. So look, these are two different approaches. Now in a GATE exam practice, I cannot take a steam table and tell you, because time is very limited. So actually GATE exams are simpler than your university exams, because they give you all the data that is required. In university exam, you need to go, mostly what they do, they actually give you the whole steam table. So you need to see what is the temperature and pressure, and then you have to find out enthalpies. Okay, so that is time consuming. In GATE, it does not happen. In GATE, they directly give you data. At this temperature and pressure, this is the enthalpy. Okay, you see RSC questions, you see all these questions, they will give you, whenever it is converted into liquid to vapor, they will give you the data. Whenever you are working in the mixed zone, okay, so they will give you the data. Okay, so sir, how to solve Rankine cycle numericals? Because of in university exam, Rankine cycle numericals data comes from steam table. On the other hand, GATE type questions is come as university questions. No, I mean, look, I hope that I have answered your question. Okay, so university, usually what they do, that they give you the steam table, and you have to filter out your information from there. In GATE, they give you directly the data. Okay, it's a very different approach for university and GATE. Okay, now this is your question number 7 and 8, that is for homework. Easy question. Do not worry about the data or the length of the question. You read the question, you filter out the information, you draw the diagram. You draw the Rankine cycle TH diagram and see what is given to you and try to, very easy question. But do not worry about the size of the question. Okay, whenever this data is given, people are just scared of seeing this data. Okay, yes. So question number 7, you have to calculate net work output. Net work output. Okay, so turbine output minus pump output, pump in, work provided in the pump, and then heat supplied also. Okay, so easy question, nothing. You have to worry about how to calculate enthalpy values, that's all. Okay, and that is also given in table. So easy question, right? Let's move on to regeneration cycle question. And very easy questions comes from Rankine and gas turbine both. Okay, now a thermal power plant operates on a regenerative cycle. I already told you what happens in a regeneration cycle. In between, you take a bleed out and the rest goes to condenser. Sometimes there are more than one exit. Okay, sometimes you bleed one more and then it also goes to open feed water heater. Sometimes what you take out is more than one streams and the rest goes to condenser. But in this particular question, what they are saying, that around 20% of the boiler steam generation rate is bleeded to feed water heater. So this is 20% of what enters. If one is coming in, then 20% is taken out, is bleeded out. Then 80% is gone to the condenser. So this 80% is coming here. And here it is mass conservation, M1 plus M2 is equals to M3. Okay. Now they are asking, enthalpy is also given, H1 is also given, H2 is also given. You have to find out specific enthalpy at state 3. Okay. Small summary of Rankine pre-superheating process. Sir, please give me small summary. You mean a written summary or what? Okay. So, now we know that we can do energy conservation here. Energy conservation. How to study cycles easily? Okay, there is no, I don't think there is an easy way, it's just the practice. Okay, I have told you already all the cycles, whether it is Rankine cycle, a gas turbine or Breton cycle, okay, or Otto cycle, diesel cycle, all the diagrams. First of all, there are few things. You should know what are the processes. You should know what are the components in the diagram. Okay, so there are mostly 4 processes. Okay, and you should know what are the processes. For example, if there is isentropic compression and expansion and isobaric heat addition and heat rejection, you know this, then all the components should be in your mind, and the TS and PV diagram, at least one diagram, TS or PV, should be in your mind. This is only requirement that should be in your mind before you go to exam. Okay, if you are still confused कि यार auto cycle में constant volume होता है, constant pressure होता है, then there will be problem in the exam. Okay, be very clear about what this cycle. These are 4 processes. These are the 4 components, and this is the TS and PV diagram. That's all. If you are very clear about this, then I don't think there will be an issue. Okay, so energy conservation you can do. Energy conservation you can do. How do you do that? Energy conservation is energy 1, whatever is coming in, plus energy 2 is equals to energy out, which is energy 3. Okay, so this is M1 H1 plus M2 H2 is equals to M3 H3. Okay, now I know everything. What do I know? This is 20% of the total mass. H1 is given to me 2800. I think people have solved this, right? 720 is the answer, right? Yes, 720 is H3. Both are easy. It's just able to look. Sometimes TS diagrams are easy because isentropic processes, it gives you more clarity. Okay, sometimes isoenthalpic process expansion happens in VCRS, so that is easy because you know H3 is equals to H4. Okay, so whatever serves your purpose, that is basically easy. Okay. Now M2 is 0.8 into H2 is also given 200. M3 is 1. Total is 1. And H3, and people have calculated, Kanil and Bhavya have calculated, is 720 kilojoule. Okay, per kg. Right? Very easy question. Look, regeneration looks to be a difficult topic, but they usually ask very simple questions from it. You go and check the previous year questions from regeneration. This cycle looks complicated. You see the TS diagram, so many lines there. Okay, but the question is very easy. Question is, concept wise, I think drawing TS diagram is little complicated, but the question is easy. Okay. Now gas cycle. Now I hope you all remember what is gas cycle. Okay, I hope you all remember what is gas cycle or Breton cycle. So we have a compressor. What is the time? Okay. Okay, anyway. So air enters or gas enters and goes out. Then it goes to a combustion chamber. Okay, I am not writing combustion chamber for a reason. Then it goes to a turbine and then it goes out. Now this is the open cycle. Actually this is the Breton cycle. Okay. Now this is combustion chamber and this is compressor and this is turbine. Now what you do, you apply some air standard assumptions, which is, do not assume we assume that there is no combustion chamber, we are adding heat at constant pressure. So instead of this, we assume it is a heat exchanger. By applying air standard assumptions, we assume it is a heat exchanger and we are adding heat at constant pressure. Second thing, we assume it is a closed cycle. Okay, so we close them together and we assume that also heat is going out at constant pressure. Okay, this is also a heat exchanger. Okay, this is your Breton cycle or gas turbine or gas cycle, whatever you want to call it. Okay, now what is the TS diagram? By compressor you are giving work, it is isentropic compression. This is isentropic expansion. Okay, so if you ask me draw the TS diagram, how will I draw? This is this diagram. Okay, so 1 to 2 is isentropic work in, 2 to 3 is constant pressure, P2 is equals to constant, and heat is supplying, you are supplying Q in. 3 to 4 is work output isentropic compression, isentropic expansion, I am sorry. And 4 to 1 is again P1 is equals to constant and heat is rejected. Heat is rejected. Yes, look, Sachin, what actually happens is, here we have to teach a lot of things in a very small time. And in that app, we had a lot of time in our hand. So we explained it by taking a lot of time. Okay. Yes, I'll just tell you, just wait. Okay. Just to give you an introduction about this. Now, let's read the question. So in a simple Breton cycle, the pressure ratio is how much? Pressure ratio is P2 by P1 is 8. Let's say pressure ratio. At the entrance of the compressor, turbine is, so we have given T1 is equals to 300 Kelvin and T3 is 1400 Kelvin. Okay, entrance of compressor and turbine. Both compressor and gas turbine have isentropic efficiencies equal to 80%. Okay. Now again we need to know, sir told to be a, yes, I know, just okay, this is also important. Okay, now they are saying isentropic efficiency is 80%. That means we have to consider isentropic efficiency. Now what happens? Now this 1 to 2 is isentropic process. It is the ideal condition. I am assuming my compressor has 100% is 100% isentropic, but they are saying the isentropic efficiency is 80%. That means this line will not be straight. okay, its entropy is going to increase. So this will be your actual process 2 dash, not 1 to 2. 1 to 2 dash will be your actual process in the compressor. In turbine, again entropy is going to increase. Do not draw it like this. Okay, do not draw it inward. Entropy is going to increase. Okay, so it will be like this. So this is your 4 dash. Now your actual expansion is 3 to 4 dash. Your actual compression is 1 to 2 dash. Is this clear? Now, so isentropic efficiency is not 1, it's 80%. If it is 1, that means it is a straight line. For the gas, assume a constant value of Cp is this. Ratio of specific heat gamma is also given, 1.4, and neglect change in kinetic and potential energy. Okay, so now 10th question. Power required in the compression in kilojoule. Power required in the compressor. Okay, so actual power you need to find out. Now we know, very quickly solve this. Okay, now what do we know? Efficiency, isentropic efficiency of compressor is 80%. And what is it equal to? It is equal to W ideal upon W actual. Because in compressor, ideal work is less. Ideally you have to give less work. Actually you have to give more work. So that is why it is ideal by actual. So W actual we need to calculate. W ideal will be equal to Cp. What Cp? What is ideal? Ideal is 1 to 2. 1 to 2 is ideal. Actual is 1 to 2 dash. Okay. So this is T2 minus T1 upon, or I can say, I don't know if you already know this, H2 minus H1 upon 0.8, or I can say Cp T2 minus T1 upon 0.8. Now, I think people have already calculated T2 because I don't know T2, right? But I know P2 and P1. So what can I do? It is isentropic compression. Process 1 to 2 is isentropic compression. So I know that T2 by T1 is equals to P2 by P1 gamma minus 1 by gamma. I know gamma, I know P2, I know P1, I know T1, I can calculate T2. So T2 is how much? T2 is how much? Can you tell me how much is T2? T2 is 543, huh? Yes, T2 is 543. T2 is equals to 543.43 Kelvin as Canil has calculated, no? Yes, Bhavya, that is also true. Now I know everything. I know I can just put it here. So Cp is work actual. Cp is 1, I think, no? 1 was given. Yeah, 1 kilojoule per kg. 543.43 minus T1. T1 is how much? 300 upon 0.8. And as you have calculated, it is 304.3 kilojoule per kg. That is correct. Okay. Canil, yes, I think Canil calculated. 4 dash we can calculate, but right now we do not need this, so we are not calculating. Although later on we will need that. So abhi hame zarurat nahi hai. We don't need that. Okay. We can directly calculate like this. Okay. Now you can also do that. You can also do work actual is equals to Cp T4 dash or T2 dash minus T1. This also you can do. Same thing. You will get the same answer. Okay. Now, next is thermal efficiency of the cycle we need to calculate. Thermal efficiency you need to calculate. Okay. Calculate thermal efficiency. Thermal efficiency, how do you calculate thermal efficiency? This is the cycle. Thermal efficiency will be net work upon heat supplied. Net work upon. There is only one tip, practice. Okay. When you start practicing, Okay, calculate efficiency. Network efficiency is equals to network upon Q supplied. Network is what? Turbine work actual minus compressor work actual. Actual compressor work we have already calculated. And heat supplied is how much? Heat supplied is, where are we supplying heat? From 2 dash to 3. 2 dash to 3. So this is also equal to Cp T3 minus T2 dash. Now you need 2 dash actually. Okay. 11th is A. Very nice. A is correct. Did you solve it now, or have you already solved this question? Because if you have solved it now, then it is very impressive. Canal, very nice here. I mean, okay. I think I gave you enough time if everyone has solved this. Okay. Now actual work we can calculate it. Okay, nice then. Baba, very nice. Okay. Now we can also calculate actual work in the turbine like we calculated in compressor. Okay. So turbine efficiency is again 0.8. Now here what actually happens is actual work out is less than the ideal work. So now actual work is equals to 0.8. Ideal is how much? Cp. What was that? 3 to 4? No, 3 to 4, yes. So T3 minus T4. Okay. So T3 was known to me. T4 I think people have calculated earlier when I was reading the question. So how much was T4? T4, how much was T4? T3 I think was 2000, no? 1400, okay. 1400, how much was? 898. 772 was the temperature, yes. 772 was the temperature T4, na? So I think Canal, what have you calculated? What is 898 yaar? Okay, T4 dash. T4 dash again I have not calculated. You can do that, it's same only, okay. So this will, because anyway you have to use isentropic efficiency to calculate that T4 dash, no. So we can use it like this as well. Okay, so actual work that you have gotten for turbine is 501.7 kilojoule per kg. And bus now you need to calculate T2 dash as well. T2 dash as well by the isentropic efficiency, and you can calculate the, so isentropic efficiency of compressor is equals to, so isentropic efficiency is equals to ideal upon actual. You can see Cp T2 minus T1 upon Cp T2 dash minus T1. Okay, Cp and Cp will cancel and you can get T2 dash. Okay, T2 dash is how much? 604. You can get T2 dash 0.28 Kelvin. And now everything I know here, I can put and I calculate efficiency, which I think people have already calculated. Canal, Bhavya have, I think Sachin also had calculated 11th A. Yes. 0.248, so 24.8 is the efficiency. Okay, now let's move on to the next question. Okay, now what is this? Consider a gas turbine. Now I know the diagram, I know the TS diagram as well. Both the diagrams I know, the construction diagram and TS diagram. So I will not draw the construction diagram, maybe I will draw the TS diagram to explain. Okay, a simple gas turbine is there, gas turbine cycle with perfect, okay, I need to draw the TS diagram. Perfect regeneration. Do you know the concept of regeneration, or do I need to draw the diagram here? If you only say, then I am going to explain the regeneration diagram. Otherwise, I will just draw the TS diagram. TS diagram is this. Okay, 1 to 2 and 3 and 4. Do you want me to draw the regeneration diagram, or we can work with the TS diagram only? Now what actually happens? Are you telling me, or should I move ahead with the TS diagram? TS diagram is okay, then ठीक है. Okay. Now what actually happens here is that whatever comes out of the turbine, okay. So you see this is coming out of the turbine. This is coming out of the turbine. Now what we do is we take it and we send it here, and then we give it here. Okay. And here we use a regenerator. Here we use a regenerator. So this is 1, this is 2, let's say this is A, and this is 3, 4. So here we have 4, here we have B, let's say. Okay. So if I draw the regenerator, I can draw it like this. These are the gas coming. It is 4, it is B, and this is going in the combustion chamber 2 and A. Now very important condition here is, I always share Sachin. After the class I share the PPTs. Okay. After every session usually I try to share it. Okay. Now very important condition here is that T4 will always be greater than TA. Otherwise there is no point in using the regenerator. Also TB will be greater than T2. These are the two very important conditions for regeneration. Okay. You do not know, okay, it's mechanical by Vipin Yadav. Okay. Now, so when it entered, you see that it cannot go, so TB, okay, it cannot go above this point. Similarly, this is A. I don't know if it was A or B, let me check. 2 to A, okay, 2 to A. This is A and this is B. Okay, so T4 is always greater than, what is that? Yeah, T4 is always greater than TA, and TB is greater than T2. Okay, your temperature A, this point can never be above T4, and this it will be less or equal to. Now if it is equal to, that means perfect regeneration. Your regenerator is perfect. It has 100% effectiveness. Okay, so all the heat transfer is happening between the exhaust gases and the incoming air. Okay, so this is the case of perfect regeneration. If it is not, if it is imperfect, then your A point will be below. A point will be somewhere here, and your B point will be somewhere here. Okay, now this is the case. So they are asking the ratio of thermal efficiencies. I need to find out. 0.8, is it correct? Let me check. 0.8 is absolutely correct. 0.8 is absolutely correct. Now we have a Breton cycle and then we have a regeneration cycle. They are asking us to compare their efficiencies. Okay, and they are giving both the cycle. Pressure ratio is 6, P2 by P1 is 6, ratio of specific heat is 1.4, and ratio of minimum to maximum temperature is this. So they have given P2 by P1, this is P2, this is P1, P2 by P1 is equals to 6, pressure ratio RP, and they have also given temperature ratio minimum to maximum is how much? How much is 0.3, and gamma is 1.4. Okay, so now we all know how to calculate Breton, simple Breton cycle efficiency. How to calculate this? It is 1 minus either T1 by T2 you can say, or you can say 1 minus RP gamma minus 1 by gamma, or you can say 1 minus 1 by RV What is this? RV is equals to V2 by V1. Okay? RV gamma minus 1. Any formula you can use. Ratio पूछा तो भाव्य simple और regeneration का. Yeah, we have asked the ratio of the efficiencies of Baraton and the regenerative cycle. So RP also I know. So can you calculate this? RP is 6. RP is 6. Okay? RP is 6. So you can calculate this. What about regeneration? Regeneration cycle. So regeneration cycle is what? Regeneration is 1 minus. It's basically, I don't know what is the efficiency. So I will start it net work upon Q supplied. Now net work I can write supplied minus rejected. So it will be 1 minus Q rejected upon Q supplied. You should always know the formula, the AND formula you should know. I am telling all this just to, if you do not know this, just to clarify ki how it came. Okay. Now 1 minus, what is the heat rejection? What is the heat rejection? Now you see. Now I am only supplying heat here. Q supply, Q in is here, and this is the Q out. Okay, I am only supplying heat from 3 to A point and rejecting from B to 1 point. Okay, so now this is what Q rejected is Cp, or I can say H B minus H1, and this is supplied is T3 HA. Okay, is this clear? Now this is equals to Q rejected by Q supplied. Okay, now I can also do this T2 minus T1 upon T3 minus T4, because HA is equals to H4 and HB is equals to H2. Now I can take some, now there is a whole derivation for it. I am not going to do that, but when you do that, you will get T1 by T3 RP gamma minus 1 by gamma. ठीक है? Gamma minus 1 by gamma. Okay? Now I know everything. I know T1 by T3. This is already given to me as 0.3. RP is known to me. This is 6, and gamma is also known to me. So tell me how much is this. First of all, tell me how much is the Baraton cycle. 0.4, was it 0? Yes, 0.4. And this is 0.5, as I can see you have calculated. This is 0.4. Yeah, this is 0.4. I'm sorry. So when you do that, you do the ratio of Baraton and regeneration of Baraton. You will get 0.4 by 0.5. Okay, 0.8. Okay. Yes, 0.40 and 0.5, 0.49. Okay. Now, this is your homework. Question number 4. I have already given you 3 questions as homework. I am not sure. Oh yeah, 3 I have given. Yeah. So this is your from gas turbine homework. Okay. Do this. Now let's move on to the psychrometric question. Okay. Very quickly, I want answers from you. I am going to move aside and I am going to give you this. This is your dry bulb temperature. Okay. Very quickly, how many people have already done the refrigeration and air conditioning? If you have done it, very quickly tell me what is the correct option. Okay. 0 to 1. 0 to 1, what is happening? Okay, 0 to 1 is a horizontal line. Okay. 0 to 1 is a horizontal line. 14A. Why A? 0 to 1 is a horizontal line. It's a constant specific humidity. Yes, B is correct. B is correct. Okay. 0 to 1 is what is happening. Temperature, dry bulb temperature is increasing. Okay. Dry, no, not A, not A. Okay. So dry bulb temperature is increasing. Only temperature is changing. There is no change in the specific humidity. Okay. There is no change in the specific humidity. So that is sensible heating. No latent component. Okay, no latent component. So this is sensible heating. Okay, 0 to 2. 0 to 2 is what happening? Heating is happening, but specific humidity is decreasing. Okay, heating is happening, temperature is increasing, but specific humidity is decreasing. That means what? Specific humidity is decreasing. That means what? That it is dehumidified. When the specific humidity decreases, that means you are removing moisture. Okay, so now this is your also called as chemical dehumidification. Okay, then 0 to 3. Now 0 to 3 you are going, if this is your reference, you are going this side. This side means temperature is decreasing. But again what is happening? Your specific humidity, I am really sorry, I am hiding what I am writing. Okay, specific humidity also decreases. So this is the case for cooling and dehumidification. Cooling and dehumidification. Okay, so now this is I think 3. Okay, now 0 to 4. Now again you are going this side. Okay, you are going this side. So temperature to decreasing, but specific humidity increasing. So it is, we will talk about this. What happens here? What is happening with 0 to 5? 0 to 5, you are going that side. So if you are going that side, your, what is happening? Your temperature is increasing and your specific humidity is also increasing. Now when specific humidity is increasing, then I can say it is humidification for sure. But because 0 to 4 temperature is decreasing, that means you are doing water injection. Okay, and in 0 to 5 your temperature is increasing, that means you are doing steam injection, because steam has higher energy, higher temperature. Okay, so steam injection. So this is this and this is this. Thank you, Meenu. Just, I mean, it should be clear for you people, that's all. Okay, I know that I write little, I mean, my font size should be bigger, but I'll okay, anyway. So the correct answer is B. Okay, now let's move on. So here we have explained all the processes, whatever happens in a psychrometric chart: sensible heating, sensible cooling. How do I draw sensible cooling? I can draw it like this. Okay, this is sensible cooling. Okay, you go that side, but horizontal line. Okay, so sensible heating, sensible cooling, cooling and humidification, cooling and dehumidification, heating and humidification, heating and dehumidification. Okay, now let's move ahead with the main question, and then you have 2 questions for homework. We will try to do one of them if we have time, otherwise 2 questions, very simple question, nothing much, nothing more. Okay, now moist air is treated as an ideal gas mixture of water vapor and dry air. Molecular weight is given at a location. Total pressure P total is given as 100 kilopascal, and temperature is at this point is 30 degrees Celsius, 303 Kelvin. Relative humidity is 0.55. Now at this temperature, saturation pressure is 4246 Pascal. Mass of water vapor per kg of dry air. We cannot use, that is difference. What is difference? Mass of water vapor per kg of dry air. So what they are asking? Mass of water vapor divided by mass of dry air. Just dry air is 1. Okay, per kg of dry air. Okay, now what is this? What is this? This is also called as specific humidity. Okay, and I can say this is 0.622 PV upon P total minus PV. Vapor pressure divided by total pressure minus vapor pressure. Okay, now I know total pressure, vapor pressure is known to me. I think take 1 second. Yeah, that is correct, 14.87. Okay, I know total pressure, but vapor pressure is known to me. Okay, vapor pressure is unknown to me. So how do I calculate vapor pressure? I know that relative humidity is equals to vapor pressure and saturation pressure at the same temperature. Okay, so here what is the saturation temperature? It is given to me 4246, and this is what 0.55. So I can calculate PV is equals to 4246 into 0.55. Yes. I mean, that is what we do. We can use 0.62 to not directly. This actually comes from solving that. No, we first of all we write that terms and then we solve this. I think we take the same values only, right? 28.84 and 18. Okay. Okay, so you can take 0. I did not pay much attention on this, but I think the answer will, okay, it's a numerical type question, so I would say yes, that is correct. You should pay much more attention, okay? Because if it is objective type question or MCQ, then you can get the most closest answer. But if it is numerical type, then pay more attention. If the value is given, it's better to calculate that, okay? Now, so PV we have calculated, very nice canal, that is something that I missed. Okay, I shouldn't miss that. Now, PV you have calculated. PV is how much? PV is 2335.3 Pascal. Okay, so now you know PV, you can just go here and you can put this and you can calculate your specific humidity or the mass of water vapor per kg of dry air, but you need to calculate that in gram, not in kg. So whatever you are going to get, multiplied by 1000. Okay. So 14.87 you have already calculated, and this is 14.87 grams of water vapor per kg of dry air. Okay. Similar question is there, just little bit of, thoda ghuma diya hai bas, it's the same only. You can try this. Last question, I'll give you some hint. Okay, I'll give you some hint. So what is happening here is that they are giving that a moist air is entering in a cooling coil. So let's say this is my cooling coil. Okay, now it is entering here. Now pressure is given, temperature is given, and relative humidity is given. Then it is going out here. Also, they are saying saturated. So here we have a value of X. Here it is saturated. So X is equals to 1. Okay. Exit pressure is given, temperature is given, relative humidity is not given. Okay. So that will be 1. Now the saturation pressure of water. Now here saturation pressure is also given at 30 degrees Celsius, and here also saturation pressure is given. Everything is given. Molecular weights are also given. Mass of water condensed. So what is happening? A mixture is coming. A moist air is coming. Outside saturated air is going. So what happened? Some water vapor is condensed in the cooling coil. Okay. So whatever is going here, some water vapor is mass of water vapor, something is condensed. Okay, how do I calculate this? So mass of water vapor condensed is equals to whatever specific humidity entered minus whatever specific humidity went out. And we all know how to calculate specific humidity. All the parameters are given to me. I can calculate that. Very simple. Okay, so this is your last question for homework. Okay, and also this question 15th and 16th. So today, out of 17 questions, I have given you 6 questions as homework. We have solved 11 questions. Okay, and I hope that you had a good practice session, right? And we will also keep coming up with this. So we will close the session here. Sachin, if you are there, still there, this is my Telegram group. You can join this channel. I'll share the PDF of this session. Okay, whatever modifications I have done in front of you, so you can see, because I have changed that Baraton cycle. I have made it from the normal cycle to the regeneration cycle. Okay, so mind that. Otherwise, I'll share the PPT, solve the questions, and put the share the answer in the Telegram group. We will see if you have any doubts. Okay, So let's close this session here. Thank you very much for being here. Right? Thank you.